okay? All right, so like I was saying before, so you guys did trig just out in space. Now we're going to take our trig and we're going to put it in a coordinate system, okay? So this is a circle within the coordinate system. The center is 0, 0, okay? So you're looking at a circle in your Cartesian coordinate system with a center 0, 0. It turns out also that your circle has a radius of 1. So the coordinate of that point there is 1, 0. Which means that if I was to draw a radius here, it has a length of 1, right? Since it's a circle, all the radii are the same. When we do something like this, we call it that is called the unit circle. Yeah. So what we're going to make right now is called the unit circle. We're going to actually derive the whole thing. We're going to make it from scratch. So here we go. Unit circle, guys. So I can actually make a right triangle out of this, right? We aren't talking about triangles, right? So there's a right triangle. My hypotenuse is 1. If this is theta, right? Theta is our reference angle. If that's theta, then x is my adjacent, and my y is my opposite. And that means that this point must have the coordinates x, y. Right? Because this length is going to be that distance from 0, right? And this length y is going to be that distance from 0. That's how you count it. Yes.
Oh, wait.
The hypotenuse is length 1. Yeah. Okay. You guys remember our friend SOHCAHTOA? Yeah? Which means that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. That's what SOHCAHTOA means. I'm going to assume that you know SOHCAHTOA. Y'all are friends.
Harper's class.
All right. So, because of SOHCAHTOA, I can actually represent my x and y coordinates in terms of trig functions. Okay? So, let's look at what is cosine of theta in this case. Okay? So, my little triangle that I made here with sides 1, x and y. Cosine of theta is, what is it? It is adjacent, so x, right, over hypotenuse, which is 1. So that's x over 1, which is x. Hey. So what is that? That means that my x coordinate is cosine theta. So I could say that this has, I could represent my x coordinate as cosine theta because of that. What is sine of theta? Well, sine is opposite over hypotenuse, so that's going to be y over 1 or a y. So that means that I can represent the coordinates for my unit circle as x can be cosine theta and y is sine theta. Fantastic. Awesome. All right. Now, what I really want to know is I want a numeric value for this x and y, for this particular x and y, if theta is 45 degrees. And it is actually possible for me to figure out the exact x and y coordinates of those two for theta equals 45 degrees. So I'm going to take this triangle right here, and I'm going to take it out. And it's going to look like this. So this right here is our new triangle. It's a special triangle. Right? It's 45, 45, 90. Hey, if this is a 45, 45, no, sorry, it's not a special triangle, but it is a, yes. Which means that these two are the same, right? So now x and y are the same. So we'll just call them both x. Right? And then our hypotenuse is going to be the square root of 2x. And I could justify that for you a little bit. Imagine, if you will, that I took a triangle that had, if this was 1 and this is 1, right? Then it must be the case, and this is not our unit circle, we're going to have something a little smaller, right? This length is not 1 and this length is not 1. It's going to be a little smaller. But if that's true, then this has to be. What are we doing? I'm just showing you where this one comes from. Okay? I didn't want to just throw it out there and not justify it. Okay? So, using my Pythagorean theorem, it turns out that should be that if I wanted to find out what that is, right? It would go 1 squared plus 1 squared equals c squared. So 2 equals c squared. So c is going to be the square root of 2, plus or minus, but there's no such thing as negative, right? So that means that this must be root 2. But we're not sure. But it's not length 1, right? So check it out. If I make these each x's, right? Each one of these x's, I'm actually dilating this, right? By some factor of x. I'm taking this triangle and I'm dilating it by some factor of x. So I can represent this as our actual triangle. They're not the same triangle. I'm trying to show you where the root 2 comes from. Because I could just, sorry, that root 2 doesn't look very good. I could dilate this, right? Just by adding a factor of x. And I'm going to wind up with a similar triangle. And it turns out that this similar triangle right here is the same as the triangle that we had in our coordinate system. That's going to allow us to actually find the coordinate. So let's go ahead and do that. So we can find our x coordinate. Our x coordinate is going to be cosine of theta. All right? In this case, theta is 45. All right. So cosine of theta. So cosine is opposite. Sorry, adjacent over hypotenuse, right? So this is our adjacent. That's our hypotenuse, right? So we have our adjacent. This is our hypotenuse. So all right. Well, the x over x is 1, right? So is it fair that I say that that becomes 1 over the square root of 2? Okay. We don't like radicals in our denominator. So what we have to do is rationalize it. The way that I do that is by multiplying by special number 1. If I multiply this by the square root of 2 over the square root of 2, it's going to make it so that I don't have a radical in my denominator. I don't want a square root in my denominator. It's just not proper. So 1 times square root of 2 is square root of 2. And the square root of 2 times the square root of 2, that's the square root of 2 squared, right? What happens when you square a square root? It goes away. So what I just found was the x-coordinate of our triangle back here. So I found this. So this is root 2 over 2. Now we just need to find the y-coordinate. So we need to find sine of theta. So sine is opposite over hypotenuse, so that's going to be again x over root 2x. So that means they're going to be the same. Yeah? We don't have to calculate it again. We know that they're the same. Yeah. Yeah, you could say that. You could, yeah. I just want to be comfortable with the. Here. What do you think? Yeah. Yeah. Actually, you need to look at this real quick. All right, so let's put that in there. Awesome. Using a similar process, I can also find those coordinates. So now what I made is, so for this, so this, I'm looking at this angle right here, which is going to be 60 degrees. And if that's 60 degrees, then that means that this must be 30. So now I have a special triangle. I got a 60, 30, 45 triangle. which is this one right here. So I pull this one out, it's going to look like that. The 2x, x, and the root 3x comes from the idea of the ratios of the sides of special triangle of this special triangle. If you were to look at special triangles, you'll see that for one value of x, these will always be true. Because it follows this, we can go through the process again and find cosine of theta. So theta is 60 degrees. So cosine is adjacent over hypotenuse. Which is going to be 1/2. And that's our x coordinate, right? And sine of 60 degrees is going to be opposite over hypotenuse. And there we go. We found our x and our y coordinate of each of these points for our 60-degree triangle. So this has the coordinates 1/2 and root 3. The last one we can find is for theta equals 30 degrees. And this is the triangle that we formed. Yeah. Well, isn't that the same thing as, it's the same triangle, right? Just transformed? Because isn't it the case that that our height is the same thing now as our length over here? So then that coordinate, I can just flip them. Because our 60-degree, our triangle with theta equals 60 degrees is the same as our triangle with theta equals 30 degrees, just flipped and laid on its side. See it? Once we've found all of those, it's easy to find all of our coordinates for these points in our other quadrants. This one is at, okay, so if we went 30 this way, we're going 30 this, if we went 30 that way, we can go 30 degrees this way. This is 90 degrees, right? So that will bring me to 120 degrees there. And then if I went 15 degrees that way, I'll go 15 degrees this way to find my next, which is 135. And that means that this one must be 150, right? Once you get all that hard work done in quadrant 1, the rest kind of unfolds, right? The x coordinate now is going to be negative, but it's the same. And the y coordinate will be positive. For here, our x coordinate will be negative. Y coordinate positive. You can keep going through this thing, right? Down here in quadrant 3, both your x and your y coordinates will be negative, but they'll be the same. if you're going to follow the same pattern. It follows a nice, neat pattern. And I'll give you guys a printout of one of these, all super nice and neat and beautifully put together so that you can reference it. But you guys will actually make one tomorrow. And then I'll give you a really nice one.
So make a pattern.
Yeah, or keep one you really like. Okay. Now that you guys have seen the unit circle, you understand that we're talking about coordinates. So hey, so now I could say something like, hey, what is sine of 135 degrees? You can, but if you have this in front of you, it's quicker to say, hey, remember, sine is your y coordinate, right? Yeah? So what's your y coordinate of 135 degrees? And it's root 2 over 2. Yeah? So if I was to say, hey, what is cosine of 120 degrees? We're looking at the x coordinate at 120 degrees, and that would be negative 1/2. So now you can go through this and find exact number values for trig functions. Yeah, you can put it in your calculator, but the thing is your calculator is probably not going to spit out square root of 2 over 2. It's going to give you the decimal value of it, and there's a good chance that if you're being asked this on like a test, they're going to want your answer to be an exact value, not a decimal. Okay? And so the next element to our unit circle is breaking it up into pi radius. And that's what we're going to do right now. And I was sure that I had... You guys ready to do some fraction work? So, same circle, unit circle, okay? This is the same circle. Except now we're going to talk about it in terms of rotation, okay? Whenever we're going around the unit circle, we always go counterclockwise, all right? We start at 0 degrees. Because the way they set it up, I'm not sure why. And we move on, and we keep going. You guys remember that your circumference of a circle is equal to 2 times pi times r, right? 2 pi radius. Or you can also do the diameter, right? So, in this case, the radius is equal to 1, right? Right, we said our radius was 1. It's a unit circle. Radius is 1. So the circumference is 2 pi. So if I go all the way around this thing, start at 0, go all the way around, I come back to 2 pi, right? So one full rotation is 2 pi. So then what's half of a rotation? If a full rotation is 2 pi, then half a rotation is pi. What's a quarter of a rotation? Yeah. So this right here is, or we could call it pi over 2, right? Okay. Then how about down here at the bottom? It's, well, but you're past pi, right? So it's like pi and a half. So, how about 3 pi over 2? Okay, yeah.
3 over 2, like the 3 pi over 2, the pi in the numerator.
Yes. Pi will always be in your numerator of these, never in the denominator. All right, so now that means we can probably figure out like that one, and we can figure out that one,
So are
right?
those like the angles?
They are. These correspond with the angles. So it turns out that 90 degrees is the same thing as pi over 2. So what we're doing is we're now representing angles in terms of rotations around the unit circle, instead of just using degrees, we're using what's called radians. So these are radians, and I'll talk about how we convert from radians to degrees. We're kind of getting there. We're almost there. We're almost at the point where we're coming up with the idea of how do you convert degrees to radians. So here we have, if we're going a quarter of the way, right? That's going to be, I want to put it over here. That's pi over 4, right? Which means this one is 3 pi over 4, right? Because we're 3/4 of the way. And now we've come to, so and I guess we could continue on here, right? We could go down here. So pi and a quarter. Huh? Yeah. Pi over 4. And then pi and 3/4. No, we're at yeah, pi and 1, 2, 3/4. Huh? 7 pi over 4. And these again are all degrees, and we're about to put that together right now. How are we going to do this one? Okay, so I'm going to say, okay, that's 30 degrees. I would like to know what that is in terms of pi, in terms of like the ratio of segments, you could say, or rotations around this circle. Okay. But what is pi? If this whole thing is 360 degrees, right? A circle is 360 degrees. Then this here is 180 degrees, yeah? All right. Well, what portion is this 30 degrees of this 180 degrees? The way that you can figure that out is just by making the ratio 30 over 180. That's 1/6. So if we're saying that this piece right here, that this 30-degree slice is 1/6 of that half, right? We said that the 1/4 was 1/4 of the pi, right? So it makes sense to say that this is pi over 6. And that actually leads us right into how to convert from degrees to radians. You would put, so to convert, I meant to put it in there, I swear. There we go. Yeah, that's right. You're going to take your degrees. That's 5. That's it. What if we wanted to go backwards? What if we wanted to convert pi over 6 back to degrees? Someone says, hey, your angle theta is pi over 6. You'd like to know what your degrees are. Well, how would you reverse that process? Yeah. So you would do, so from radians to degrees. You're going to do radians. That's what I had written down in the first 6 minutes, and I don't know why. I'm second guessing all of that. So let's do it. Let's convert pi over 6 to degrees. We converted 30 degrees to pi over 6. Let's go the other way around. And that's it. There we go. We're going to make our own unit circle tomorrow, and we'll be converting from degrees to radians and radians to degrees. But that right there is trig circle in a nutshell. So it's our unit circle in a nutshell.